Good afternoon, and thanks for the opportunity to share with you the latest progress on our project. This is the last year of our project. We've done with our experimental campaign, trying to wrap up our data interpretation and analysis and also publications. I would like to acknowledge my graduate students, Milad, and also Atul and Mohamed, graduate students at UCSD and Professor Gamal at UCSD. And also I would like to acknowledge Peer for funding this project, the staff at the Powell lab at UCSD, and also Ramjack, our industry partner. I'll do a very quick background, and then I'll provide an overview of our testing program. I'll focus more on the series number 2 of our testing, which included the mitigation measures, and also I had to, because of time limit, pick some example results and also some conclusions. Anyone who has attended or seen Professor Bray's presentations on this topic would know well about this story. Great example from the Tohoku 2011 earthquake, building multi-story building on a shallow foundation, settling 70 centimeters, building next door on a pile foundation, basically not settling, and free-filled, seeing about 30 centimeters of settlement. So there is a factor greater than 2 between free-fill and that low-rise building. So if you are wondering how significant damage in terms of dollar amount of these type of buildings are, maybe single building may not be that significant, but once you multiply by thousands of houses like this that happen in Japan, in Christchurch, the dollar amount does become significant. Example from the 1994 North Sea earthquake, not liquefaction related, but it's still just a great example that the residential buildings did play a significant role in terms of dollar property damage. More liquefaction-related example. This is from the 1989 Loma Prieta earthquake. With all respect for our structural colleagues, so if someone looks at this example, may say that this is a structural failure. It does. The second floor was damaged, but this was a 3-story building, and the first story was damaged because of the liquefaction, and this is happening in Marine District in San Francisco. Past several years at the UNR, using our shaking table facility, we've looked at how to, improve the resiliency of the lowest story residential type of buildings. We started this around 2013. I had a master's student looking at liquefaction-induced settlements, and then looking at the model of buildings. And then for past couple of years, we've started looking at cost-effective measures to reduce those settlements. And the example that I will be presenting today is the project we use helical piles to reduce those building settlements. And this is the focus of this study, and we will be looking at other mitigation strategies in future as well. So this topic has been investigated by different ways, different approaches. Started with the 1964 earthquake in Niigata, and Tokimatsu and Yoshimi in 1977. They published the first paper on it, on the topic, based on the case history data, and also supplemented with the 1G testing results, and made some conclusions, observations. And then there was an earthquake in Philippines in 1990. Dobry used that data and then added some centrifuge test data on the results and made some conclusions. And then Professor Bray at Berkeley has been studying this topic for several years, and at UNR we've been using 1G testing setup to do to look into this phenomenon. So I would like to finish up this slide with a quote from Professor Ei, who has develop simulated laws for both bungee testing as well as centrifuge. That there's no perfect solution. We just need to know the limitations and advantages of the methods we utilize. When it comes to the 1G testing, we would like to go as big as possible, but of course there is a downside in terms of budget and number of tests we can do. I'm going to show you a wide range of examples of 1G testing, from largest, test facilities at E-Defense. The height of the soil box is 5 meters, the length is 16 meters, and then the second one is the NERI facility at UCSD. The height of the laminar box 4.7. Another laminar box at the UCSD Powell lab. The height of the box is about 3 meters, and then the scaled facility rigid box we have at UNR. So for the purpose of this project, looking at the low-story buildings, shallow liquefiable soils, we utilized this box. This was based on our observation from past earthquakes. A lot of cases exist in literature. Shallow liquefiable soils, maybe just a couple of meters in thickness, causing problems. So we felt that this box was the sweet spot on this curve, and cost-wise, and also the number of tests we can do. And based on Professor Elgamal's presentation this morning, we did learn that from this box to this box, even though the height-wise maybe the difference is 2, but cost-wise the difference can be 6 times more expensive. As a part of this project, we did 2 series of tests. Back in 2018, we did our first test. I'm going to refer to it as a baseline test. In that test, there was no mitigations implemented, and that test was the basis for the blind prediction as a part of peer, and I did presentation on that during the last annual meeting, and we announced the winners. And then in April 2019, we did our second series of tests, which included a mitigation measure, and we used the helical piles as our strategy. For each testing, we ran a series of tests, changed the PGA, played a little bit with the level of groundwater table. What we had as our target input motion was a sinusoidal type of input motion, frequency 2 hertz. Testing was relatively simple. Footing, we placed the weights on top of footings to represent the contact pressure of a low-story building, about 800 PSF. We had 2 feet of crust, and then about 4.5 feet of loose sand, liquefiable layer, and then a couple of feet of dense sand at the bottom. I did mention about that the sweet spot on the cost versus size, and this was what we felt that we could still use the facility, do enough number of tests, and still be representative of true cases out there. And then for the series number 2, we had a group of helical piles attached to the footing, and we wanted to look into the performance. So this is the 10, almost 10 feet in height, the laminar box at the UCSD's Powell lab. Some challenges we had. I'm going to talk more about the instrumentation. We wanted to make sure that when these piles are instrumented, they survive when they are being driven into the ground. We had some lessons learned from some other colleagues. I'll mention about that. So we had to go through a tedious, time-consuming procedure to how to install the strain gauges on these piles. The design of pile footing connection, we use bracket connection. That was also a challenge because the ram jack or even other contractors, they have all these nice, beautiful tables for the capacities, but they are all for axial. There is no specification for lateral design. So there was a big question mark how, if those connections would survive the earthquake loading. For strain gauges, this is before we installed the strain gauges, after we installed the strain gauges. Some photos of how we did some welding around each location, did different gluing, and then covering with foil tape. We learned about this type of detailed instrumentation from Professor Serrato of University of Oklahoma. She had done testing on very similar, helical pile, but in dry sand. And we received the call. She was saying that you need to be very careful, otherwise a lot of the strain gauges were going to be damaged during installation. So we got lucky. We went through time-consuming process, of course, but then majority of our strain gauges, I guess we might have lost a couple of channels of data. And then this is the final instrumented piles, relatively easy installation. This is one of the benefits of helical piles that we could install. This is when the foundation was placed, and then we attached the helical piles, mimicking underpinning existing foundation systems. Some more photos of that connection. This is the completed model. The model before shaking. This is I'm going to show the. We took so many videos of intentionally picked this one. This is the test, the benchmark test. There is no helical pile. We'll watch this one first. We'll see how it settles, and then we watch from the same angle the second test. See that the foundation just basically sinking. And once the shaking is stopped, even you can tell that the settlement continued. And that was now the second test, exactly same angle. This time, footing was supported on a group of helical piles. Let's see why this is not shown properly. Yeah. Sound works, but. Let's see if we can show using this. I don't know why this is not working, but what happened was we had less than an inch settlement of the foundation, which was what we were hoping for. We were very I was personally very nervous in the morning, and then what I wanted, especially to link this discussion to the previous presentation, was once the shaking stopped, a lot of ejecta coming from this side of the foundation. So that was really what I wanted to show. Couldn't show. But I have a photo to show. The model before shaking and after shaking, ejecta continued coming out of the ground after the shaking stopped. A closer view of that ejecta. Again, this was a very important component of our research, and also what we were hoping to do. Reproduce what we see in the field and from reconnaissance. The piles were extracted after the test, no observed damage or plastic deformations. That was good. CPT, we use CPT, characterize the model before the first shake, after every shaking. I had to pick some example results to show. The first one I picked was the large bending moment at the boundary between dense layer and also the liquefiable layer, again, consistent with what people have reported, whether from 1G testing or centrifuge. The second example may look busy, I'll spend a minute to explain. Please pay attention to the blue curve, which is associated with the left y-axis. This is showing displacement of the foundation. You see that between these two dashed lines, which is during the shaking, we saw the largest portion of the displacement, but once the shaking stopped, settlement continued. So we attributed these part to both the continued volumetric induced settlement as well as the ejecta-induced settlement. Whereas the red curve, which is the foundation settlement with helical piles associated to the right y-axis, only during the shaking we had some maximum about half-inch settlement, and then once shaking stopped, since the volumetric ejecta did not contribute because of the helical piles pinned in the dense layer, there was no settlement. The settlement is stopped. Some quick observations. Helical piles perform very well in terms of reducing the settlement significantly from 27 centimeters to less than 1.5 centimeter, and also no damage to them. We were hoping, and we achieved extensive liquefaction and sand ejecta. We continue doing interpretation of the data. The test series 1, which was done last year, we've completed the data interpretation, and the results were submitted for publication. And I also wanted to highlight that the scale testing on a shallow foundation in liquefied soil, 1G testing setup, this test was the first of its kind, and so hopefully that will yield to future opportunities. And also the fact that industry support was extremely important. I can't emphasize enough. Given the limited budget, without their support, probably I couldn't do this presentation today, so I need to really acknowledge that one. And also the fact that these type of collaborative projects are really unique in terms of opportunities, complementing the expertise. Of course, coordination is important, but in my opinion, they are great opportunities. And nobody beats happy faces at the end of the day, and we have the people from Ramjack coming from all around the country to see the test, and hopefully, and thankfully everything went well. Thank you.